ferromagnetic materials strongly gets magnetized. They get strongly magnetized in the direction of the external magnetic field. That is the reason why they get so easily and strongly attracted to the external magnet. Suppose if you bring a magnet and if you keep a ferromagnetic material, whatever is the direction of the magnetic field, suppose if you bring north here, it will also magnetize in the same direction, like this is north and this is south. Hence this south gets attracted to north so strongly. So reason why they get strongly attracted can be explained by the existence of domains. Let us try to here have a quick comparison of para and ferromagnetic material. In paramagnetic material, actually in case of diamagnetic material, individual atoms do not have dipole moment. In case of paramagnetic materials, individual atoms have magnetic moments, but they all are randomly oriented. So because they are all randomly oriented in different directions, the net magnetic moment of the paramagnet is zero, even though every atom has magnetic moment. Here also in ferromagnet also every atom has magnetic moment, but here they form groups which we call domains. See, individual atoms have magnetic moments, but individual groups of atoms, they cooperate among themselves, which we call coupling mechanism. They form a group. Within this group, which we call domain, these groups we call domains. In this domains, the magnetic moment all aligned in the same direction. If you look at an adjacent domain, not necessarily in the same direction, but in different direction, but all the atoms, individual atomic magnetic moments are all in the same direction. You take another domain and all of the magnetic moments. So even though the magnetic moments are aligned in different direction, in groups they are aligned in different direction. In this case also, here the entire material as a whole, we call it specimen. Specimen magnetic moment is zero. Similarly, for this domains also, specimen magnetic moment is zero. So specimen magnetic moment is zero. But here individual atoms have magnetic moments, they are randomly aligned. When heated up and because of the thermal agitation, they won't be able to align themselves. Because when you apply a magnetic field in a particular direction, let's say in this direction, the domain in that direction started growing. That means this will occupy this, this will occupy this. This will influence this, this will influence this. And finally, if you see, the size of the domain increases and all the atomic magnetic moment in the domains are in the same direction. That is why ferromagnetic materials are strongly magnetized in the direction of the external magnetic field. The ferromagnetic materials, there are two types. There are hard ferromagnets and soft ferromagnets. Example of a hard ferromagnet is very simple. Let's take the case of iron, cobalt. You know that iron, cobalt, all those materials are attracted by attracted to the external magnetic field. But the point is, when you remove the external magnetic field, they again go back to the same stage. So they have individual domains and those domains magnetic moments are arranged in a direction. But hard ferromagnets, they retain the magnetism and they have they have net magnetic moment. So naturally occurring lodestone or alnico. So alnico means aluminum nickel cobalt alloy. So alnico and lodestones. So alnico and lodestones are actually hard magnets. So the magnetism persists even after it is removed. Okay, but this particular thing, let's say cobalt, iron and all those things, once removed, this will be coming back to the same stage. So the relative magnetic permeability is greater than 1000. If you saw, relative magnetic permeability is 0 or less than 1 for mu r is equal to 1 plus chi, and chi being negative for a diamagnet, and here chi is positive in case of a paramagnet, but this value is large positive. Hence this ferromagnets have large positive values of relative permeabilities as well as chi values. So but the magnetic property, okay, this magnetic property strongly dependent, actually ferromagnetic property depends on temperature. Okay, so at high temperature ferromagnet becomes a paramagnet, and then the susceptibility decreases with increase in temperature. For instance, this can be put as Curie-Weiss law. The susceptibility of a ferromagnet is C by T minus Tc, where Tc is the Curie's temperature. Curie's temperature. So what happens is, at Curie's temperature, the ferromagnetic substance become a paramagnetic substance. So ferro becomes para at Curie's temperature. For example, if you take the case of iron, if iron is heated to about 1000, actually 1000, roughly 43 Kelvin, or roughly about in Kelvin it is 1043, it's roughly about 900 degrees Celsius. When you heat it up, iron becomes a paramagnet. And if you take the case of a cobalt, so you just need to heat up even further, 1394 Kelvin, it becomes a paramagnet. Once it becomes a paramagnet, the susceptibility is inversely proportional to temperature. So ferromagnetic property depends on temperature, paramagnetic property depends on temperature, and the susceptibility is kind of inversely proportional to temperature. And you just think of gadolinium, just about 317 Kelvin, which is roughly about the room temperature, and it is less than that it was a ferromagnet. Then after that it becomes a paramagnet.